Okay, so good morning, everyone. Today I'm going to talk about the stochastic field effects in the Ising model, symmetry breaking and symmetry restoring. And this is a work that I have done in collaboration with Raul and Amit Chakrabarty from Kansas State University. So here there is a summary of what we are going to see today. I know that many of you are already familiar with the Ising model, but first of all, I will do a quick reminder. And then I will introduce our model, which is basically the Ising model under a time-dependent but uniform in space magnetic field. And although the Ising model has been studied for many years and in many different forms, we will see that our model, which is a very simple model, it leads to very interesting results, or at least to us. In particular, we will identify three different phases in the model, and then we will analyze the transitions between them. And finally, I will show you a mean field description of the model that reproduces the behavior that we see in 2 dimensions. Okay, so the Ising model is a model of interacting magnetic spins. We have a square lattice with n spins and periodic boundary conditions, and we assume that each spin can take the values -1 or +1, and the energy of this system is given by this Hamiltonian here. We assume that the coupling constant J is positive, so that the interaction between the spins is ferromagnetic and the system minimizes its energy when the spins are aligned. So, for temperatures above the critical temperature, the thermal noise dominates and the system is disordered or in a paramagnetic phase. But then, as we decrease the temperature, the system spontaneously chooses one of the 2 ordered states, and the spins align either in -1 or in +1. And we have an ordered or ferromagnetic phase. The order parameter of this model is the magnetization, and here you can see a plot of the magnetization as a function of temperature. In the ferromagnetic phase, the magnetization is non-zero, and then in the paramagnetic phase, the magnetization is 0. And because this transition from non-zero to 0 is continuous, this is a second-order phase transition. Perfect. So, our goal in this work is to study the Ising model under a time-varying but uniform in space magnetic field. So now we will have this additional term here in the Hamiltonian. There are several works in the literature that have incorporated such fields as, for example, oscillating fields or random fields. But the thing is that most of these works, they only focus on the analysis of the order parameter, which now is defined as the time-averaged magnetization. And we think that if you only focus on this quantity, you are missing very interesting information about the system. And we will see that if you analyze the probability distribution of the magnetization for different system sizes, you can get more insight into the phase behavior of the system. So in our model, this time-dependent but uniform in space magnetic field is a random field that is Gaussian distributed with 0 mean and variance 2D. We assume that the system is in contact with an isothermal bath at temperature T, and to simulate the evolution of the system, we use a heat bath dynamics. So at the beginning, we randomly set the initial configuration, and then at each step, we randomly select a spin and we assign it a new value +1 or -1 with these probabilities here. After n spin updates, which constitute 1 Monte Carlo step, we randomly select a new value of the random magnetic field independent of the previous one. So the idea is like this. We sample an initial value of the random magnetic field H0, we perform n spin updates, we sample a value of the magnetic field H1, we perform n updates, and so on. Okay, so now let's see what are the results in our model. In particular, first we want to identify the different phases, and then we want to analyze the transitions between them. So, in order to identify the different phases, first we are going to look at the probability distribution of the magnetization. So in the numerical simulations, we let the system evolve, and then after a thermalization transient, we measure the magnetization and we determine its time average stationary probability distribution. We will focus on moderate values of the field intensity D, because for large values of the field intensity, we observe a very rich and non-trivial behavior that we have not analyzed in this work. So, first of all, we are going to look at the probability distribution of the magnetization at temperatures close to the critical temperature of the field-free Ising model, okay? So here we have the field-free Ising model, whose results are well known. And here we have two system sizes, 50 and 200. First, what we can see is that for temperatures below the critical temperature, as for example 2.1, this one here, there is a single peak at a non-zero magnetization value, and this peak becomes sharper as the system size increases. Then, as we approach the critical temperature and we go, for example, at temperature 2.2, we can see that in the small system there are jumps between the two ordered states of the magnetization, but in the large system we don't see that jumps, okay? And now, if we go to temperatures above the critical temperature, as for example temperature 3, we can see that we have a single peak around the disordered state of the magnetization, and this peak again becomes sharper as the system size increases. So, in the limit of infinite system size, we recover the usual picture. That is, for temperatures above Tc, we have a paramagnetic phase characterized by a delta distribution centered around m equal to 0, and for temperatures below Tc, we have a symmetry breaking ferromagnetic phase characterized by a delta distribution centered in one of the two ordered states. Okay, so now let's see the results for the model with a random magnetic field. Here we have the results for two field intensities, 0.1 and 0.6. And the first thing that we can see is that we have a transition between a unimodal and a bimodal regime at the same critical temperature of the field-free Ising model. But however, there are a lot of differences with respect to the case with no random field. The first thing that we can see is that in this case, for all temperatures, well, for the temperatures considered here below the critical temperature, there are jumps between the two ordered states of the magnetization, even for the large system size. And then for temperatures above Tc, we still have a single peak around m equal to 0, but now the distributions are much wider than before. And now here it comes a very important thing. And this, that note that the vertical scales of the two plots for the two different system sizes, the vertical scales are the same. So this means that in this case, the distributions show practically no dependence on system size. And this result suggests that even in the thermodynamic limit, we will obtain wide distributions. So in the limit of infinite system size, we expect this behavior. We expect for temperatures above the critical temperature a soft paramagnetic phase characterized by a broad probability distribution around m equal to 0, and for temperatures below the critical temperature, a soft ferromagnetic phase where the symmetry between the two ordered states is dynamically restored, and therefore the probability distribution has two broad peaks around the two ordered magnetization states. Here, I would like to say that we haven't seen in any work that they report the existence of these two phases. Maybe it is reported somewhere, of course, but we haven't found it. And also the existence of these two phases, I mean, two phases such that the probability distribution is wide even in the thermodynamic limit, for us, this has been a very interesting result and surprising. And if you are not very convinced of this idea that we get limiting wide distributions, I mean that the distribution in the thermodynamic limit is wide, here there is some more evidence. Here you can see probability distributions both in the soft para and in the soft ferro phases for field intensities 0.1 and 0.6, and we have for system sizes. So here, for example, in this case, we have that this is the system size 50, 100, and then 300 and 500. So you can see that as the system size increases, the distributions reach a limiting shape. Perfect. Now let's look at the probability distribution of the magnetization at temperatures significantly below the critical temperature. Here we have the results for a field intensity 0.1, and here we have two temperatures, 1.6 and 1.7. First, at temperature 1.7, which is the pink curve, we see that the system is in the soft ferromagnetic phase, because we can see jumps between the two ordered states, and we see that the distributions show no dependence on system size. But now, if we go to a lower temperature, at temperature 1.6 in blue, we can see that in the small system there are jumps, but in the large system there are no jumps. So at this temperature, the system is in a bona fide ferromagnetic phase. It's true that if simulations were run for a longer time, it's possible that we would also observe jumps at a temperature 1.6 for the large system. And that would mean that at this temperature, we are actually in the soft ferromagnetic phase. So what we can say is that for the observation time considered in the figure, which is 10 to the 8 Monte Carlo steps, there is a transition between the soft ferromagnetic and bona fide ferromagnetic phase in the temperature range between 1.6 and 1.7. Okay? And then I will talk about the dependence of this transition on observation time. Now, if we go to a field intensity 0.6, here we have the probability distributions for temperature 0, and we can see that in this case, we are in the soft ferromagnetic phase even at 0 temperature, because we have two peaks and no dependence on system size. So for this field intensity, the ferromagnetic phase is not exhibited at any temperature, and for all temperatures below the critical temperature, the system is in the soft ferromagnetic phase. So we have seen the different phases in the model, and now I will show you the maxima of the probability distribution as a function of temperature, and in this way we will get a more clear picture about the different phases in the model. These black dashed lines represent the Onsager's analytical solution for the model for the field-free case, okay? Now we will represent the different phases in this way. We will use two symmetric open circles in the case of a ferromagnetic phase, two colored symmetric circles in the case of a soft ferromagnetic phase, and a single colored circle centered around m equal to 0 in the case of a paramagnetic or soft paramagnetic phase. So here we have the data for a system size 50, for a system size 200, and what we see here is that in the case of d equal to 0, that is the field-free Ising model, we only have the ferromagnetic and paramagnetic phases. For a field intensity 0.1, we have the ferromagnetic phase at low temperatures, then we have the soft ferromagnetic phase, and for temperatures above the critical temperature, we have the soft paramagnetic phase. And then for field intensities 0.6, we only have the soft ferro and the soft para phases. And here also it's interesting to note that in the model with a random magnetic field, the curves also fit the Onsager's analytical solution for the field-free case. Okay. So we have seen the different phases in the model, and now we can construct the phase diagram, and also we can analyze the different transitions between the phases. So here we have the phase diagram, we have temperature as a function of field intensity, and let's see what's happening here. Okay, here this is the behavior, the well-known behavior for the model with no random magnetic field. In this case, there is the usual symmetry breaking phase transition between the paramagnetic and the ferromagnetic phases. And then in the model with a random magnetic field, this transition transforms into a noise-induced transition between a soft paramagnetic and a soft ferromagnetic phase. This transition occurs at the same critical temperature of the field-free Ising model and is not characterized by a symmetry breaking in the thermodynamic limit, because here we have the soft ferro phase in which we have a restoring of the symmetry between the two ordered states. And then in the model with random field, we also have at lower temperatures a new phase transition between a soft ferromagnetic and a ferromagnetic phase. This transition occurs at a temperature that decreases with increasing field intensity and disappears for field intensities larger than 0.6, more or less. Then I will tell you how we obtained this line separating the soft ferro and the ferro phases. But first, let's try to get some insight into this transition here between the soft ferro and the ferro phases. So, in order to classify this transition between the soft ferro and ferro phases, the first thing that we do is to look at the order parameter, which is defined as the time averaged magnetization and can be computed from the probability distribution of the magnetization in this way. Here you can see the absolute value of the order parameter as a function of temperature for two field intensities, 0.1 and 0.6. So, the upper branches correspond to the ferromagnetic phase, where the order parameter is non-zero, and the lower branches correspond to the soft ferromagnetic phase, where the system can jump between ordered states, and therefore the order parameter is zero. Okay, it's difficult to say, but it seems that the transition is discontinuous. And if we make a zoom of the plots, you can see it even more clearly. So, this transition is discontinuous. Now, the natural question is whether this is a first-order phase transition. In order to determine if this transition is first-order, what we are going to do is to look at the fourth-order Binder cumulant, okay? The Binder cumulant is this quantity here that depends on the fourth and second moments of the magnetization. And the thing is that in a first-order phase transition, the Binder cumulant behaves in this way. That is, there is a deep minimum of the fourth-order Binder cumulant near the critical temperature for large system sizes. This is how does the Binder cumulant behave in a first-order phase transition. And now, here we have the results for our model. We can see that in our model, we don't have any of these minima. So what we can say is that our transition is discontinuous, but it doesn't fall into the standard classification of first-order phase transitions. So the transition between the soft ferro and the ferro phases is discontinuous, but it's not first-order. Instead, this transition is characterized by a divergence of the escape time from a completely ordered state of the magnetization, okay? More precisely, what we have here is we have a trajectory of the magnetization as a function of time, okay? What we do is to define the jump time tau as the time the system needs to cross the barrier m equal to 0 when starting from the completely ordered state -1. So, in the soft ferromagnetic phase, the system can jump between ordered states of the magnetization and the jump time is finite. But in the ferromagnetic phase, once the system enters into an ordered state, it cannot escape. So the jump time tends to infinity. So in this way, the transition between these two phases is characterized by a divergence of the jump time. And now I want to show you a plot of the jump time as a function of temperature, okay? This vertical line is the critical temperature of the field-free Ising model, and we have the results for two system sizes, 50 in blue and 200 in pink. First, I'm showing you the results for a field intensity 0, I mean for the field-free Ising model. In this case, there is no transition between the soft ferro and the ferro phases because the soft ferro phase doesn't exist. But anyways, I would like you to see how does the jump time behave in this case. So in this case, we see that the jump time diverges at Tc because here we are entering into the ferromagnetic phase, so the jump time diverges. And what we see is that at all temperatures, the jump time for L equal to 200 is larger than the jump time for L equal to 50, okay? And now, let's see what happens in the model with a random magnetic field. Here we have the curve for a field intensity 0.1, and first what we see is that the jump time is independent of system size for most of the temperatures considered here. And then we can see that the jump time diverges when we approach this vertical line that is more or less 1.7, and that's because when we approach this line, that is the line that separates the ferromagnetic phase from the soft ferromagnetic phase, so the jump time diverges, no? And now if we move to a larger field intensity, 0.7, in this case we see two things. First, that the jump time is independent of system size at all temperatures, and second, that the jump time doesn't diverge at any temperature. And that's because for this field intensity, there is no ferromagnetic phase. And for all temperatures below the critical temperature, the system is in the soft ferro phase. So there is no divergence of this quantity. Okay, so now we can understand how we can obtain this line here in the phase diagram separating the ferromagnetic and the soft ferromagnetic phases. This line separates the region where the system can jump from m equal to -1 to m equal to 1 in a time less than 10 to the 8 Monte Carlo steps, which is the soft ferro region, from the region where the system cannot perform this jump, that is the ferromagnetic region. If we repeat this simulation for different observation times, we get different curves. This curve, green or yellow curve here, is the curve for the smallest observation time, 10 to the 5, and this black curve here is the curve for the largest observation time, 10 to the 8. We can see that as the observation time increases, the area of the ferromagnetic region decreases. We cannot rule out the possibility that in the limit of an infinite observation time, the ferromagnetic region would disappear. But we think that this is an unlikely scenario, and moreover, 10 to the 8 Monte Carlo steps is already a long observation time. So for all practical purposes, the system exhibits both the ferro and the soft ferro phases. Now, finally, I will very briefly explain a mean field description of the model that reproduces all the results that we have seen in 2 dimensions. So the basic idea of the mean field description is that each spin interacts not with its 4 real neighbors, but with average neighbors. So this sum here over the 4 neighbors of a spin I is replaced by 4 times the average magnetization per spin of the whole system, okay? And if we introduce the variable n that represents the number of spins in state +1, we can rewrite this quantity here in this way. And we do it in this way because n is a discrete variable while m is a continuous variable, and it's more comfortable to work with a discrete variable. So here we have the probabilities that when we select a spin I for making an update, it chooses the values +1 or -1, and in the mean field approximation, we approximate this probability here that contains this sum, we approximate it in this way. Okay, so we have this information here, and then on the other hand, we can write the Chapman-Kolmogorov equation for the evolution, for the time evolution of the probability distribution that there are n spins in a state +1. I don't want to bother you with the details of these equations, but then if you have questions, you can ask, of course. But the thing is that we have this Chapman-Kolmogorov equation, and then we can write it in compact vector form in this way. where now this P is a vector whose components are P of 0, P of 1, P of n, and W is a matrix whose elements are the transitions probabilities that we have here. And sorry that I forgot to say that all this approximation of the mean field theory, we have this probability here that then enters here in these transition probabilities. So this is encoded in this matrix W here. So now what we are going to do is to numerically solve this equation by iteration. And we have to take into account that this matrix W depends on time because it depends on these probabilities that depend on the random magnetic field. And we have to update the magnetic field at each Monte Carlo step. So we want to iterate this equation. We are going to make an iteration, and what we do is, first, we propose an initial guess for the probability distribution, and we sample an initial value of the random magnetic field. Then we iterate this vector of probabilities n times, and this constitutes one Monte Carlo step. Then we sample a new value of the magnetic field H1, and we iterate this vector of probabilities n more times. We continue this procedure, and then after discarding a thermalization transient, we compute the time averaged probability distribution. Once we do this, we can try to reproduce all the behavior that we had in the two-dimensional case. And it turns out that we obtain the same qualitative behavior. That is, we observe the soft paramagnetic, the soft ferromagnetic, and the ferromagnetic phases. The maxima of the probability distribution as a function of temperature in the model with a random magnetic field also fit the analytical solution for the field-free case. We can also draw this line in the phase diagram separating the ferromagnetic and the soft ferromagnetic phases. So we reproduce all the behavior in 2 dimensions. And as all the results that we have in 2 dimensions, all the results are numerical because we don't have any theory. For us, it's good to have this mean field theory that reproduces the same behavior because it provides additional evidence, no? So, to finish the presentation, I will make a summary of what we have seen today. Today we have studied the Ising model under a time-varying but uniform in space Gaussian random magnetic field. We have identified 3 different phases in the model, the soft paramagnetic, soft ferromagnetic, and ferromagnetic phases. And in particular, we have identified these 2 new phases, okay? These phases are characterized by broad probability distributions even in the thermodynamic limit. And additionally, in the soft ferromagnetic phase, we have a restoring of the symmetry between the 2 ordered magnetization states. We have seen that the usual symmetry breaking phase transition between a paramagnetic and the ferromagnetic phase of the field-free model transforms into a noise-induced transition between the soft para and the soft ferro phases. And this transition occurs at the same critical temperature of the field-free model. Then, at lower temperatures, we have seen that there is a new phase transition between the soft ferro and the ferro phases. We have seen that this transition is discontinuous, but is not first order, and instead it's characterized by a divergence of the jump time tau, that is the time needed for the system to escape from a completely ordered state of the magnetization. And finally, I have shown you a mean field theory that reproduces the same qualitative behavior than the 2-dimensional agent-based model. And finally, as future work, it would be interesting to study the role of the correlation time of the magnetic field, because in this model we have assumed that the magnetic field changes every 1 Monte Carlo step, but it would be interesting to consider other correlation times. And also it would be nice to see how do the results change if we introduce a bias field in addition to the random field. So that's all. Thank you very much.
Are there any questions here in the audience? Okay. Yeah. Very nice, very interesting.
Thank you.
So this transition is not first order, not second order. Can you say anything else? So that it has hysteresis? Not at all?
We have not studied this. It would be interesting to study it. I mean, we haven't focused on that. What we think is that simply it doesn't fall into the standard classification, and its critical behavior has to do with this jump time. And
All right. Have you checked so when you are in the soft? So that was
yes, I can put the phase diagram because
exactly.
or maybe
when you are in the soft paramagnetic and the transition is from soft ferromagnetic to ferromagnetic.
Yes.
So in the soft ferromagnetic, the system, you make a trajectory of the order parameter, it crosses zero.
I have some trajectories of the magnetization here. So you are saying in the soft ferromagnetic.
Soft ferromagnetic, exactly.
In this case, you continuously have jumps between the
from +1 to -1, no?
Yes. And here you can see what is, I think it's surprising, that for a field intensity 0.6, even at temperature 0, you have these continuous jumps.
Exactly. And in the trajectory to the ferromagnetic, from soft ferromagnetic, you have that you compute some of this waiting time, no? So you can define from those trajectories, you can define a mean time for the jumps. This is what diverges.
Yes, I mean, what it diverges is that, well, precisely, if you start the trajectory from -1, in this case, for example, if you start the trajectory from here, it will remain here forever.
So
this is what
you check just one time, just one.
No, well, to obtain this line, what we do is that for example, we are at this value, field intensity 0.3. We go to one temperature and we see if there is a jump or not. We go to another temperature and we see if there is a jump or not. And we increase the temperature until we find the first temperature where we have a jump, no?
Yeah.
And we repeat this procedure 10 times.
Okay.
I mean, this curve is the average of 10 realizations.
You saw a picture of the divergence of the time, no? For this case, or you didn't do that?
Sorry. Okay, sorry. No.
I want the divergence from the other side.
I was confused. I think you are referring to this?
Yes, exactly. How you compute those, exactly. How you compute that?
This is the average of 10 to the 3 or 4 jump times. I don't, to compute these times, what I do is, you are asking this?
Yeah, I'm asking this because so when you are in the soft ferromagnetic, this continues to jump up and down.
Yes, so, okay.
So if you look at the time you are in the phase, the average time you are in a phase, is that what diverges?
Yes, the average time that you are in the ferro phase, it diverges.
Larger and larger.
Yes. Sí.
Yeah, okay. It's similar. It's related.
It's not the average time of one.
I might have we talk later. I might have a suggestion for this.
Okay. Thank you.
Any other questions?
Thank you for a very nice talk. My question is about exactly this slide. What happens when this vertical line hits the y-axis?
When the vertical line hits?
Y-axis, yes. At which d it happens?
Sorry?
I mean, you have a different d, you have this vertical line which separates ferromagnetic and soft ferromagnetic phases, yes? Or I'm confused?
I mean, for example, to see if I am understanding you, for this field intensity 0.1, this would be soft para, soft ferro, and ferro.
Yeah, and you have this vertical line.
Yes.
Yes. And with increasing d, this vertical line moves to the left.
Yes.
What happens when this vertical line hits?
Okay, so as you increase this field intensity, this vertical line moves to the left, and you can see that the divergence of the jump time occurs at lower temperatures.
Yes.
But then when you reach this axis,
at which d?
when you reach this axis, what happens is what we can see here. That
I don't think so, because between 0.1 and 0.7 there are big region. What happened at 0.5?
At 0.5, let's imagine, you would have something like this. You would have a curve that diverges super close to the y-axis.
Yes, but at some g it will diverge exactly at 0 temperature. And this is kind of critical d. What is this critical d?
This critical d, we don't have the exact number, but more or less is 0.6. Because at field intensity 0.6, well, I don't know how to show it, but for a field intensity 0.6, there is no ferromagnetic phase. So if you had 0.6, I didn't plot it here because I don't have the data, but for 0.6, it would be more or less the first field intensity for which the jump time doesn't diverge at any temperature, because this vertical line has moved, and when you reach this axis, it doesn't diverge anymore because you don't have the ferromagnetic phase anymore. So as you don't enter the ferromagnetic phase, you don't never enter it, the jump time doesn't diverge, because the jump time diverges when you enter into the ferro phase. But if you don't have ferro phase, you don't have a divergence.
This critical temperature has some status. You wrote 2 points and some digital numbers. And this critical field has some status or not? Can it be predicted from some exact theory?
No, sorry, did you ask if we can predict?
You have critical temperature at 0 field.
Yes.
And it's kind of constant. It can be calculated from some exact theory, blah, blah, blah. Can you calculate, or somebody, critical field in the same manner? You said it's around 0.6.
Yes.
But 0.6 and extra digitals, it can be calculated. Doesn't matter.
Oh, numerical.
No, she said around 0.6.
Wow.
Okay.
Yeah. Because 2 point something is very precise, I guess.
Well,
Okay. Thank you.
analytically,
Yeah.
Well,
Thank you.
analytically, we have an idea how to do it. And numerically, this, we could always improve the numerics.
yeah, we could do something more precise. That is, we set the temperature to 0, and we change the field intensity, and we look at the first time where we can jump from -1 to +1, so we are in the soft ferro and not in the ferro phase. We could do something like that and have a more precise estimation of the field intensity.
Looking at this, I say you could have, might have a divergence at negative temperature, right?
Well.
Could be, I could do in the mean field, we do that. Instead, not here, not in the Monte Carlo, but in the mean field to see where it diverges at a negative temperature. Okay. Anybody from the Zoom has any questions?
Yes, okay. Can I have one or two?
Okay, but Tobias, go ahead.
Yeah, so one is, have you tried it? I would like to sort of understand a bit better the mechanics of this, right? So what I don't know if you've done this, right? Run the system without the field, say in the ferromagnetic phase, and let it sort of reach the ferromagnetic state, and then switch the field on.
Okay.
And then what happens? So then you have these domains that form, and then I guess they somehow dissolve, no? Well, I don't know. It would be sort of, that shows you the effect of the field, right? And I expect that the spins that are first affected are the ones at the boundaries between sort of up and down, no, domains. I think, no, but I don't know. That's a suggestion more than a question. I don't know if you've done that or.
So your suggestion is to turn on the field once you are into a well-defined phase, let's say,
just
no?
to understand what physically is happening because of the field, right? I would sort of run the system without the field until it has reached sort of the stationary state, and then activate the field dynamics, and then see how what happens then, right? What are the effects of this field, right? In a spatial system, maybe even, right? So I don't know.
I think it's an interesting suggestion, and also we are now starting to make some plots of the spatial distribution of the magnetization to get some more insight on what's happening here, and it would be very interesting to see how does this thing behave in that case. Yes, so thank you.
And the second thing is, so I think, so what the effect of temperature in these systems is to allow spins that are, so say you have a spin that is mostly surrounded by down spins, right? At zero temperature, that spin can only be down, I think, right? So, and temperature means that nonetheless, the spin can also go up, right? Non-zero temperature. And the random field has a similar role, right? Because if then the sign of the field is such that it points sort of in the direction of telling the spin to be up, the spin can also go up, even though all surrounding spins are down, right? So it makes me wonder if the field strength can somehow effectively be absorbed into temperature. So that you can redefine temperature and say that the total temperature of this is the actual temperature plus something that comes from this randomness of the field. Now, I don't know, right?
I don't know because one more,
because that's sort of
since you have for a fixed value of D, you have two different transitions with temperature. I
don't know.
I don't know. But well, clearly there is here a competition between disordering effects. That's clear, but I haven't think of it in this way. I don't know.
This value 0.6, so this is the strength of the magnetic field, no? Of the varying up and down. That's enough to flip the spins? No. Or is it?
The field, this field?
Yes. So for temperature, for zero temperature.
Yes, yeah.
If you put all of them at -1.
Yes.
Then that value is the one that is allowed to jump.
Yes.
And that's the critical point.
It's the critical point because it means that is the first noise intensity, the first field intensity, such that it's able to promote jumps even at zero temperature. Yes. Yes.
So you can compute that analytically. Is that?
Well, analytically, we don't have any theory. Numerically, we could try to estimate this D more precisely. We haven't tried to get the super.
The temperature is not just the amount of field you need to flip.
Yes, but we don't have any theory.
Constant field maybe increase, and the jumping time is more than what the bubble step.
Yeah.
So you have many field values in jumps. Okay. There are no further questions. Pablo Roger says very nice, Sarah.
Thank you, Pablo.
Okay, we thank Sarah again.
Thank you. Moltes gràcies.